Hi guys. We're in the middle of Christmas vacation now, and I'm not here today simply because on Christmas Eve my dad was diagnosed as having cancer in the bladder, and I am gone today because I am with him. He is being operated on today. So what I'm going to do here for Chapter 6, we're going to do a very fast review, and then we're going to get into the new stuff like electronic dot diagrams, which are kind of fun. Okay, so in looking at the basic review, we talked about the idea of energy. And why is it that atoms are going to bond? Well, there's two things, losing energy and gaining stability. Now, in that, we talked about this magical formula called the Octet rule, where we're talking about 8 electrons because it's about maximum stability. To this. Now, we know that atoms can give up or take electrons, okay, and the whole point is to fill that outermost shell. We looked at the kinds of chemical bonds that there were. We went with covalent, ionic, and metallic. And covalent, you can have polar covalent, nonpolar covalent, okay, and covalent bonds, we talked about how that they work, sharing of electrons, whether it's equally or non-equally. That's where we get nonpolar and polar. Okay, we looked at the nonpolar covalent bond example. It's like the 2 hydrogens, okay, nonpolar because it's shared equally. We looked at the polar covalent example with hydrogen and fluorine because fluorine has a greater electron affinity compared to the hydrogen atom. Excuse me. So I showed you guys this cartoon, the idea about this tug-of-war with the single electron that the hydrogen has. Okay, we also talked about the idea that if you've got these atoms that are negatively charged and positively charged, inevitably they're going to be attracted to each other. So we talked about how in the world we can predict the bond type. You may remember electronegativity is how well does the atom in a bond attract shared electrons. We talked about the range, as you know, and depending on that difference of the electronegativity, the bonds can range from nonpolar to highly polar to ionic. You could look at ionic as an extreme form of polar, okay, and we looked at the chart there, and we did some examples as we finished off 2015 with this. We looked at the electronegativity difference and types of bonds, and yes, I'm trying to pay attention to our timing here. Okay, now let's talk about the types of bonds that we have. Well, we have covalent bonding, where we have bonding pairs. Okay, we have electrostatic force, where positive and negative charges in the atoms, they will either attract or repel each other. Now, there are diatomic elements, and these are typically elements you're going to find in nature that they exist by themselves, and they stay together like hydrogen and nitrogen and oxygen and fluorine and chlorine and bromine and iodine. Okay, that you guys see that. Now we got to talk about dot structures. Now, the guy was named Gilbert Lewis. He's the guy who actually came up with the electron dot diagram, and it's really useful to explain what's going on with covalent bonding. Okay, because remember the idea is you have dot notation. We talked a little bit about that in the last chapter. Minimum 1 dot, maximum 8 dots, okay, and if you look here, there's a chart here that kind of reminds you about how many dots does each atom have to start with. Now, those dots represent valence electrons, right? Okay, so bonding, yeah, he invented it. I mean, he got a Nobel Prize in chemistry for this. I think it was back in 1948 or so. So let's take a look at example of number 1. Look at chlorine, okay, Cl₂. So here's a chlorine atom. Here's another chlorine atom. Now, chlorine normally has 7 electrons. It has an overall charge of 0. It's neutral. Now, is chlorine okay with this? No, it's not. Okay, why? Because its outermost shell isn't full. And that means the chlorine is going to do something very desperately to get that 8th electron. Connecting with another chlorine, pretty natural. Okay, and what you end up getting, so you have your 7 dots here, 7 dots here. Notice we've got these electrons that are red. Why? Because those are the electrons that are going to be involved in the actual bonding. So now you have 2 chlorine atoms that combine together to form a Cl₂ molecule. Okay, and in that you may notice that the 2 red dots here that I'm circling around, okay, that is the bond. That's where the bond is taking place. Okay, and this representing the two dots there, that represents a single bond. Now, that also is represented by the dashed line that you see down below. So this, the two dots, which in English looks like a colon, okay, looks very similar to is the same idea as that single dash that you're seeing. Now, usually we represent the dash, but they do represent the same thing, okay? Hydrogen's another example here that we can go through. Again, hydrogen is going to fill up, and you'd say, but wait a minute, it doesn't have 8 electrons, right? Because hydrogen is too small. The most that it can have are 2 electrons, and that's it. And that's why hydrogen can typically hook up with a lot of other atoms out there, but hooking up with itself, yeah, it does. And that also makes it very explosive. Well, why? Well, because remember, hydrogen is a very small atom, and other atoms that are bigger want the electron. So, yeah, they're going to rip it out. Ah! And that's why hydrogen blows up, for all you Led Zeppelin fans out there. Let's take a look at water. Now, water, we have got 2 hydrogens and an oxygen in there. And here, if you notice, we got the blue dot with that hydrogen, and we got the red dot with the other hydrogen, and oxygen, well, it's got green dots, and that's it. Well, when we combine it, remember, now you got H2O. Now, it doesn't tell us the shape of the molecule, it's just telling us where and what electrons are being shared between which atoms. And in this case here, for the hydrogen, if you notice, you've got the red dot of this hydrogen here that allows it to connect to the oxygen. And then you have the blue dot here for this hydrogen that connects to the oxygen. Yeah, that's pretty much it. So we also represent that with the lines that you guys can see. Okay? Now, what about diatomic oxygen? Well, here in this case, for diatomic oxygen, this is where we start getting into multiple pairs of electrons that are being shared. Okay, because oxygen normally has 6 valence electrons in the outermost layer. Okay, and I do need to take a look at my time. Okay, I'm about halfway through. Okay, so what's the purpose of this? Well, remember, the oxygens want to get 8 electrons. Okay, that's that octet rule. So how do we represent that? Well, if we look here we've got 2 oxygens. They've got their 6 electrons. You'd say, hey, wait a minute. How come we don't have the 2 electrons on the 3rd side of the oxygen, and the 4th side we just leave it blank? Well, it doesn't work that way. When you're putting in the electrons, you want to put it around. You want to start going clockwise. Think of it as a box around the oxygen atom. Okay? And then you go from there. But let's go with the theory here. So we've got these 2 oxygen atoms. They end up connecting with each other, and notice how they end up sharing not 2 electrons, but 4 electrons total. This results in a stronger bond between the 2 oxygen atoms. In other words, because it's a stronger bond, and you have 2 pairs of electrons, we call that a double bond, which makes it harder to break compared to a single bond. It's like taking a pen or a pencil and putting a second one there. It's like a double bond. It's a little harder to break than the single bond. Think about it that way. So that's where we get into double and triple bonds. Okay, so with double bonds, 2 pairs of electrons are shared between the atoms, like CO2, and there's a great example right there. And if you notice here on this, you've got the 2 dashes that represent double bonds. So wait, carbon's got 2 double bonds. Right, so how many electrons surround carbon, the carbon atom? 8, because a double bond has 4 electrons being shared, times 2 of these double bonds, and we end up getting 2 double bonds. So we end up getting 8 electrons there. Now, triple bonds, they're more rare, but they exist. Okay? There are 3 pairs of electrons that are shared between atoms, like nitrogen, N2 gas, and carbon monoxide gas. Those are also, and I'm checking a look at my timing here, okay, they also represent. electrons that are being shared. So for those atoms out there, for many of the atoms out there, the most that they can share, okay, like this in terms of bonding between two atoms, it doesn't matter if they're the same or they're not, the most that they can share, ladies and gentlemen, is basically 6 electrons, or 3 pairs. And that's where you get the triple bond. So if you think about the triple bond, again, going back to the pencil, if this is a single bond, this is a double bond, this is a triple bond. So naturally, it's going to be a lot harder to break a triple bond molecule compared to a double bond or a single bond. Okay? All right. How to create Lewis structures. Okay, I'm moving on here. I am not sure if I did a video on how to do electron dot structures, and I may just simply go ahead and stop here for this particular video. So let's just take a quick review. We talked about the idea about bonding. We know that atoms will bond because of the valence electrons. Okay, the Lewis dot structures explain to us how covalently bonded atoms are going to connect with each other. This does not work as well with ionic, so you have to stick with covalently bonded atoms. And this also goes into organic chemistry with the Lewis dot structures, okay, where each dot represents one valence electron, so we can have one pair of electrons between two atoms that are shared, okay, and that's a single bond. If it's 2 pairs of electrons, or 4 electrons total, that's a double bond. If it is 3 pairs of electrons, or 6 electrons total, that's a triple bond. Okay, and, well, I'm going to stop here. Take care.